Here is a habit so old it feels like part of the numbers themselves. The whole numbers live on a line. 1, 2, 3, marching off in a single direction, and the primes are the special ones scattered along that line. But a line is a choice, not a law. Take the same arithmetic and give it a second direction. Alongside the ordinary unit, one step to the right, add a second unit, one step up, call it I. Now every whole number has a partner. 3 becomes 3 plus 0 of the new unit, and you can mix them freely. 2 plus 3 of the upward unit is a single number sitting 2 to the right and 3 up. These are the Gaussian integers, named for Gauss, who took them seriously 2 centuries ago. They are not a trick. You add them, you subtract them, you multiply them, and everything closes up exactly the way it does on the line. Multiply 2 plus the unit by 1 minus the unit, and you get a clean Gaussian integer back every time. There is one number you need for everything that follows, and it is just the squared distance from the origin. For a point A to the right and B up, it is a squared plus B squared. The point 3 plus 0 sits at distance squared 9. The point 2 plus the upward unit sits at distance squared 5. Mathematicians call that number the norm, and it is the bridge between the flat picture and ordinary arithmetic, because the norm is always a plain whole number, even when the point is not on the line. Now the real question. On the line, a prime is a number with no factors but 1 and itself. That idea has to be carried out into the plane carefully. It survives, but it gets more interesting. A Gaussian prime is a Gaussian integer that cannot be split into a product of two smaller ones. And smaller has a precise meaning now. It means smaller norm, smaller squared distance from the origin. So a number out in the plane is prime exactly when there is no way to write it as two pieces, each closer to the origin than it is. Start with the smallest interesting one. The point 1 plus the upward unit sitting at squared distance 2, just off the origin on the diagonal. Its norm is 2, and 2 is prime on the line, so there is nothing smaller to break it into. It is a Gaussian prime, the closest one to the center of the whole picture. And here the norm earns its keep. It turns out that if the norm of a point is a prime number on the line, then the point itself is automatically a Gaussian prime. The reason is clean. The norm of a product is the product of the norms, so if a point could be factored, its norm would factor too. A prime norm cannot factor, so a prime norm forces a prime point. That single rule does most of the work. And it means the whole story out here is secretly controlled by the ordinary primes back on the line. One small bookkeeping note before going on. There are 4 trivial multipliers that never count as real factors. 1, the negative of 1, the upward unit, and its negative, the 4 points sitting one step from the origin. Multiplying by them just turns a number a quarter circle without changing its size, and 2 numbers that differ only by such a turn are treated as the same prime wearing a different coat. So take an ordinary prime and ask the obvious thing about it. It was prime on the line. The question is whether it is still prime out in the plane. For some of them, the answer is yes, untouched. Take 3. Out in the plane, it sits at distance squared 9, and there is no way to break it into 2 Gaussian integers of smaller norm. You can check by hand. The only points closer to the origin are the units and the prime 1 plus the upward unit, and none of them multiply together to give 3. So 3 stays exactly what it was, a prime now sitting on the horizontal axis. 7 does the same, so does 11. There is a rule behind which primes survive, and it is a clean split by 4s. Divide an ordinary odd prime by 4, and you get a remainder of either 1 or 3. There is no other option, and that single bit decides its fate in the plane. The primes that leave a remainder of 3, 7, 11, 19, 23, 31. Every one of those stays prime out in the plane. They are called inert, which just means untouched. They keep their place on the axis, and because the picture is symmetric, each one is mirrored straight across to the negative side as well. They stay prime all the way out, as far as you care to look. Roughly half of all the odd primes behave this way. They cross into the plane and nothing happens to them at all. The other half are not so lucky. Watch what happens to 5. On the line, 5 is as prime as anything. Out in the plane, it breaks. 5 equals the 0.2 plus the upward unit multiplied by the 0.2 minus the upward unit. Multiply those two together. You get 4 minus the upward unit times itself, and that unit squared is -1, so the whole thing is 4 plus 1, which is 5. Each of those two factors sits at distance squared 5, closer to the origin than 5 itself, so 5 is not prime out here. It shatters into a conjugate pair, 2 points, mirror images across the horizontal axis. And 5 is not special. Every prime that leaves a remainder of 1 when divided by 4 does the same thing. 5, 13, 17, 29, 37. Each one splits into a mirror pair of Gaussian primes. There is a beautiful fact hiding underneath. A prime splits this way exactly when it can be written as 2 squares added together. 5 is 1 squared plus 2 squared. 13 is 2 squared plus 3 squared. That link between splitting and sums of 2 squares is its own remarkable story, and it has its own video. Here the point is simpler. 2 kinds of ordinary prime, 2 completely different fates in the plane. One stays whole on the axis, the other breaks into a pair off it. And one last prime, the number 2, does something even stranger. It is the 0.1 plus the upward unit squared up to a turn. 2 does not stay, and it does not split cleanly. It ramifies, the only prime that does. Put every Gaussian prime on the plane at once, and a picture appears that has no equal on the ordinary line. The inert primes stand on the axes like fence posts, evenly guarding the horizontal and the vertical. The split pairs scatter through the open plane in mirrored 2s, one on each side of the axis that made them. And the closer you look, the more structure shows up. The whole arrangement is perfectly symmetric. Flip it across the horizontal axis, and it is unchanged. Flip it across the vertical, and it is unchanged. Flip it across either diagonal, rotate it a quarter turn, and every time it lands exactly back on itself. 8 different motions, 4 rotations and 4 reflections, all leave the field of Gaussian primes exactly where it was. That is the full symmetry of a square stamped onto the primes. The line never shows this, because the line has almost no symmetry to offer. The most it can do is flip a positive prime to its negative. Out here, the primes inherit the symmetry of the plane itself, and they wear it completely. In the disk of radius 18 around the origin, there are 264 of these primes, and the 8-fold symmetry holds for every single one of them. Pick any prime in the field, and all 7 of its mirror and rotation partners are primes too. It is a dense, glittering, orderly scatter, far richer than anything on the line. And it raises a question that simply cannot be asked in one dimension, a question about getting around inside it. On the number line, the primes are stepping stones in one dimension, and the gaps between them can be enormous. Out in the plane, the primes are stepping stones in 2 dimensions, and now you can try to do something you could never do on the line. You can try to walk. Here is the setup. A traveler starts at the origin, at the center of everything. The traveler may hop from one Gaussian prime to another, but only short hops. Every step must be no longer than some fixed distance chosen in advance. Call that distance the reach. The question is blunt. With a fixed reach, does a path lead outward forever, or does it eventually get trapped? Begin with the shortest possible reach that still allows a move. A step no longer than the diagonal of one unit cell. The distance from the origin out to 1 plus the upward unit. That is the tightest leash, only the very nearest neighbors. The trail sets off from the center, hopping prime to prime, and for a while it spreads in every direction, but it does not spread forever. With that shortest reach, the walk reaches points out to a squared distance of 137 from the origin, a distance of about 11.5, and then it simply stops. Exactly 100 Gaussian primes are reachable, and not one step further can be taken. Every prime past that ring is too far to hop to. The traveler is stuck. The reason the walk stops has a name, and once it is named, it shows up everywhere in the picture. It is a moat, a ring of composite Gaussian integers, ordinary, factorable, non-prime points, wrapping all the way around the region the traveler can reach, wider than the reach in every direction. Crossing it would take a single hop longer than the reach allows, and there is no prime on the far side close enough to land on. The empty water rings the traveler in. That is the whole obstruction, stated plainly. Not a shortage of primes out there, but a band with no primes at all, too thick to jump. So the obvious move is to lengthen the reach and watch the walls retreat. A step of length 2 instead, and the trapped region blows open. Now 720 primes are reachable, all the way out past a distance of 45 before the next wall. Stretch the reach to about 2.8, a single step across 2 cells on the diagonal, and the walk breaks clean out of the entire region we computed. A disk of radius 80, with more than 2,700 primes on its trail, and no wall in sight. So a longer reach beats any single moat. Every wall we found could be crossed by stepping a little farther. The pattern is seductive. Widen the reach, break the wall, escape. And it leads straight into the real question. The real question is not about any one moat. It is this: for some single fixed reach, any reach at all, as long as it is chosen once and never grows, does a path on Gaussian primes alone run from the origin all the way to infinity? The trap is subtle. A longer reach crosses the moats we found, but out beyond them, where the primes thin and the empty stretches widen, there may be a moat too wide for that reach as well, and then a wider one past that. The whole question is whether the moats keep coming, arbitrarily wide, forever ringing the origin no matter how generous the fixed reach. If the widths grow without limit, every fixed reach is eventually trapped. If the widths stay bounded, some reach gets out, and nobody knows. This is the Gaussian moat problem, and it has been open for over 60 years. People with real computers have pushed the search far past anything drawn here, crossing moat after moat, and the farthest they have ever gotten still ends at a wall. Not a proof that the walls go on forever, just the next wall, sitting there. The honest summary is short. With unbounded steps, of course you can wander out as far as you like. With a fixed reach, every search ever run eventually hits a moat it cannot cross. Whether some clever fixed reach could thread between all the moats and run to infinity, that has never been settled in either direction. So here is the whole shape of it. Take the primes off their line and set them loose in the plane, and they sort themselves by a rule as old as Fermat. The ones that leave a remainder of 3 stand fast on the axes. The ones that leave a remainder of 1 shatter into mirror pairs, and 2 ramifies alone. What they build is a field with the full symmetry of a square, 8 motions that leave it unchanged, a kind of order the number line could never show you. The primes were always richer than the single dimension we kept them in, and threaded through that beautiful scatter is a question a child could ask and no one can answer. Start at the center, take only short steps from one prime to the next, and try to get all the way out to infinity. Every reach anyone has tried gets stuck behind a wall of empty space, and a longer reach clears that wall only to find another. We can map this field to ferocious precision. We can count its primes, measure its moats, confirm its symmetry to the last point, and we still cannot say whether a traveler bound to short steps is free to leave, or trapped near home forever. The primes scattered into the plane, drew their own walls, and left the simplest question about crossing them sitting in the open, still waiting, after 60 years, for someone to find the way through.